Hello there, chemistry students. Mr. Brown here, and in this video we are going to learn about covalent bonds and Lewis structures. And we're going to talk about how covalent bonds are formed, and we're going to learn about how to predict what a molecule might look like based on the properties of covalent bonds and drawing these simple structures we call Lewis structures. I've got an example of perhaps a more complicated one here on the front page, and at the end of this lesson you should at least be able to tell me what the structure here implies. I probably wouldn't expect you to draw one like this until you took a 200 level chemistry course. We will draw some more simple ones in the course of this lesson and talk about what these lines and dots mean. So if you'll follow me along, we will learn about Lewis structures and covalent bonds. On this slide, we have some information about covalent bonds. We've learned some of this already, but as a review, we're going to remember that covalent bonds are formed when atoms come together to share one or more unpaired electrons. The number of bonds that an atom can form can be predicted by the number of electrons that it would take for that atom to satisfy what we call the octet rule. And if we remember, the octet rule says that atoms bond and gain electrons in order to try to achieve that stable noble gas configuration of having 8 valence electrons. Lewis dot diagrams help us predict how these bonds will form, and Lewis dot diagrams are formed by writing the element symbol and drawing the valence electrons around the symbol using dots. We will see some examples of those on the next slide. So here on this slide we have a periodic table and some common Lewis dot diagrams of the atoms that we have the ability to predict how many valence electrons they have, those atoms in the main group elements. We have talked about why we might not be able to predict the number of valence electrons in the transition metals, but for these atoms, we do know how many valence electrons there are. And so their Lewis dot diagrams are their element symbols with those number of valence electrons drawn around them. We will see an example of how to do one of our own on the next slide. So, as I said, we have an example on this slide where we're asked to make our own Lewis dot diagram. The question asks to draw a Lewis dot diagram for an atom of sulfur. And so if we're drawing a Lewis dot diagram for an atom of sulfur, we first start by using the element symbol for sulfur, which is a capital S. And then we put the number of valence electrons around that symbol. So sulfur is in the 6th main group column of the periodic table, so it will have 6 valence electrons. And when I'm drawing Lewis dot symbols, the way I arrange the electrons is like this. I start on the right and I put 1 electron on the right side, and then I put 1 electron on the bottom and 1 electron on the top, and on the left, and 1 electron on the top. That's 4 total, and then I'll go back around and I will start to pair them up now, 5 total and 6 total. And so this is what a Lewis dot diagram for sulfur may look like. And then we can see we would need to get 2 more electrons to get the octet rule, so we can infer from that sulfur will probably form 2 bonds with other atoms in order to satisfy the octet rule and make its molecules. Now that we've covered what Lewis dot diagrams are, let's extend that to Lewis structures. Lewis structures show us how atoms and molecules share electrons to form their bonds. Unpaired molecules from each atom are placed side by side to show the sharing of the electrons. We've got an example up here. We've got 2 free chlorine atoms, and if we show their Lewis dot symbols, each will have 1 unpaired electron. Well, free chlorine atoms like to bond with each other and share that pair of electrons there and form the chlorine 2 or Cl2 molecules by sharing that pair of electrons. 1 unpaired electron from each atom sharing is known as a single covalent bond. And when we draw Lewis structures, we'll often see that pair of electrons there replaced with a line to indicate that there is a bond between those 2 atoms. The octet rule again kind of helps us predict how many bonds each of these atoms will form. While drawing these Lewis structures, we will run into cases where we need to share more than one pair of electrons between a pair of atoms in order to get the octet rules satisfied for those atoms. When this occurs, when two pairs of electrons are necessary to be shared, we call that a double covalent bond. When three pairs of electrons are necessary to be shared, we call that a triple bond. And you can see examples of these here on this slide. The formaldehyde, the carbon and the oxygen, must share 4 electrons between the two of them for everybody to have a satisfied octet. That's just shown by the 2 lines in the double bond in the Lewis structure here. And in carbon monoxide, the carbon and the oxygen must share 3 pairs of electrons to form a triple bond in order for everybody to have an octet of electrons. So now we're going to talk about how to draw your own Lewis structures giving the formula of a simple molecule. For molecules more complex than Cl2 and HCl, those molecules you can draw out the Lewis dot diagrams and line them up something somewhat like Legos in order to figure out what the structure is. For more complicated molecules than that, it's really best to have a set of guidelines to help draw these Lewis structures, and we've got a set of guidelines here for us to do so. The first rule says to determine the total number of valence electrons. So you'll take the molecule, see what elements are there, go to the periodic table, and add up all of the valence electrons those atoms have. If there's a charge indicated, if there's a positive charge indicated, you got to subtract that many electrons. If there's a negative charge indicated, you should add that many electrons. Then you draw a skeleton structure of the molecule or ion, arranging the atoms around some central atom. So all of ours that I'm going to ask you guys to do are going to have a central atom and then stuff connected to the central atom. You should always pick the least electronegative element other than hydrogen to be your central atom. So a lot of times it'll be carbon or a phosphorus or something like that. Sometimes perhaps nitrogen. But those are generally your central atoms. Halogens are never your central atom either. They are 2 electronegative and they only form 1 bond since they already have 7 valence electrons. We will then distribute, so you'll draw the skeleton structure, and each of those lines that you draw will represent a single bond. You'll take all of the remaining electrons from your count and distribute them as lone pairs around the terminal atoms, except for hydrogen, which can't have any lone pairs because 1 bond fills the octet. Then you will place all of your remaining electrons, any that's left over, you place on the central atom. And then at that point, you evaluate to see what does and doesn't have octets and make arrangements into double and triple bonds if that's necessary to complete octets. I've got a couple of practice Lewis structures on the next couple of slides to help you clarify some of these rules. The first molecule that we are going to draw the Lewis structure for is the methane molecule, or perhaps as you may want to call it, carbon tetrahydride, but methane is the more common name for this molecule here, CH4. So we will follow the rules that we outlined on the previous slide. We'll start counting how many electrons we have to work with. Carbon, if we look at its position on the periodic table, has 4 valence electrons, and we have 4 hydrogens that each bring 1 valence electron. So we're looking at this and we now can see we have 8 valence electrons with which to build our molecule. So now we draw a skeleton structure, we pick a central atom, and we attach everything to that central atom. Remember that I said the central atom is the least electronegative element other than carbon, and so in this case, other than hydrogen. So in this case, this forces it to be carbon. So carbon will be our central element, and we will bond everything to it. Now this is the part where you stop and you do a little bit of arithmetic, and you say, how many electrons did I use to make that skeletal structure, and how many do I have left over to distribute elsewhere in the molecule? Each of the lines that I've drawn bonding the carbon to the hydrogen represents 1 single bond. So there are 2 electrons in each of those lines. There are 8 electrons total in this molecule already. We've used the 8 electrons that we have. We have 0 left over. So that should be the completed Lewis structure for methane. We do go back and check and make sure everybody has satisfied the octet rule. Each hydrogen has a bond. Hydrogen satisfies the octet rule with just 2 electrons, so the hydrogens are great. The carbon has 4 bonds. Each bond represents 2 electrons. That is 8 total. That is what satisfies the octet rule. So we feel pretty confident in saying that this is the correct Lewis structure for CH4, carbon tetrahydride, or rather the methane molecule. We have another example here. This time we're asked to determine the Lewis structure for dinitrogen monoxide, N2O. And in this example, we start with the way we always start our Lewis structures. We figure out how many valence electrons this guy gives us to work with. And so the nitrogens, being in the 5th group of the main group elements of the periodic table, both bring 5 electrons. The oxygen has 6 valence electrons. We have 16 valence electrons to work with. Our central atom is going to be one of the nitrogens. It is the least electronegative element there. That is not hydrogen, so we will draw our central nitrogen and bond everything to it. So we have our central nitrogen in the middle there with an N to the left and an oxygen to the right. And then we will distribute any remaining electrons. Those 2 bonds use up 4 electrons. We have 12 left to distribute around the terminal atoms. 2, 4, 6, 8, 10, 12. So we distribute our remaining valence electrons, and then we need to go back and figure out and make sure, does everybody satisfy the octet rule, and if not, how can we make multiple bonds between the atoms to make sure that it does. In this case, we see each of the terminal atoms, the nitrogen on the end and the oxygen on the end, has a bond with 2 electrons and 3 lone pairs for a total of 8. So each of those have satisfied their octet rules. The central atom, however, only has 2 single covalent bonds for 4 total electrons. That is not satisfying the octet rule, and so our structure is incomplete. We need to move some of these pairs to multiple bonds shared between the nitrogens or the nitrogen and the oxygen in order to satisfy the octet rule. And so you can really kind of pick, in this molecule, any of the lone pairs to slide over to the bond. So I may say this lone pair is not a lone pair between the nitrogen, it's rather a bond. Now we have a double bond situation. And if I redraw that, I take one of those lone pairs, and instead of showing it as a lone pair of the nitrogen, I now show it as a double bond with the nitrogen and the oxygen. However, if I go back and count again, I still see this nitrogen still only has 3 bonds. That's still not satisfying the octet rule. And so I need to do it again. Now, you have a choice here. You could pull from this nitrogen to make a triple bond, or you could pull from this oxygen to make a double bond. Honestly, either of these structures would be considered correct. So either of these, we've pulled the electrons from the surrounding atoms and moved them into a bond to satisfy the octet rule. In both examples, in example A here, I have 2 double bonds between the nitrogen and the nitrogen and the nitrogen and the oxygen. That's 8 total electrons. In B here, there's a triple bond between the nitrogen and the nitrogen and a single bond between the nitrogen and the oxygen, and that is also 8 electrons. Every atom in these structures has 8 valence electrons. There's only 16 valence electrons used for both of these structures. So both of these are actually a correct Lewis structure for dinitrogen monoxide. We will learn later next week how to determine which is the more correct structure. That has something to do with an idea known as formal charges, which you will be learning later. Our next example asks us to draw the Lewis structure for the molecule CH2O. And so we start, as we always start our Lewis structures, by figuring out how many valence electrons we have to work with. Carbon always brings 4 valence electrons to the party, while the hydrogens each bring 1. And the oxygen has 6 valence electrons with which to form as bonds and make these structures happen. Totaling that brings us 12 valency electrons to make the structure for CH2O. The least electronegative element there that is not hydrogen is the carbon, so it will be my central atom, and I will bond some hydrogens to that carbon along with the oxygen from the formula. I will distribute, that uses 6 valency electrons. I will distribute any remaining valency electrons around the terminal atoms. I'm not going to put them on hydrogen because they already are full with that single bond, so all 6 should go on the oxygen. I've used up all of my valency electrons. Now I need to go and make sure everybody's octets are satisfied. The hydrogens are great with 1 bond. The oxygen does have 8 valency electrons. However, my carbon only has 6 valency electrons. So I need to move a lone pair, probably from the oxygen since it's only the only one with the lone pairs, down to another bond with the carbon in order to fix that and give carbon the full octet rule. And so the real structure for CH2O please forgive the messy O there, but there is CH2. The oxygen does have 2 lone pairs of electrons. One of the 3 lone pairs has moved down into the bond between the carbon and the oxygen to form a double bond, so that we have 12 valency electrons used. Everybody has a satisfied octet. That is the correct structure for CH2O. Here on this slide, we have our first example of a Lewis structure being asked for one of our polyatomic ions. And so we're going to draw the Lewis structure for the carbonate ion, and we notice the carbonate ion has a 2- charge. So let's see how that affects our valency electron counts. We know that carbon brings 4 valency electrons with which to bond, and each of the oxygens brings 6. There are 3 of those. But we cannot forget that the 2- charge means our structure has 2 extra valency electrons. So we add 2 more into our count from the -2 charge. That's 10, 16, 22, 24 total electrons with which to build this carbonate ion. The least electronegative element that is not hydrogen there is definitely carbon, and we'll put each of the oxygens on our carbon. We'll distribute, that uses a total of 6 valence electrons. We have 18 left with which to bond, which means we can put 6 on each of the 3 oxygens. And we may notice that when we finish, we again see all of the oxygens do have a satisfied octet, but the carbon, however, only has 3 single covalent bonds, meaning it only has 6 valence electrons. It's not satisfying the octet rule. One of those lone pairs from one of the oxygens, I'll choose the top one, needs to be moved into a double bond with the carbon for everybody to have a satisfied octet. And that's how you draw the Lewis structure for the carbonate ion. Here on this slide, we have the Lewis structure for the ammonium ion this time. The ammonium ion is the one polyatomic ion that we commonly find with the positive charge on it, meaning we've lost some electrons. So let's see how that affects the electron count of the ammonium ion. So we will put our nitrogen down, and nitrogen, of course, 5th main group, has 5 valence electrons. Each of the hydrogens bring their 1 valence electron. And if we total that up, that's a total of 9 valence electrons. However, the positive 1 charge on this ion means 1 has been lost. So we have 8 valence electrons with which to build the NH4 molecule. The atom there that is least electronegative, that is not hydrogen, is nitrogen, of course. And we will bond each of the 4 hydrogens with a single covalent bond to the nitrogen. In the process, we use 8 valence electrons. For posterity, we go back and check. Nitrogen has a full octet with those 4 covalent bonds. Each hydrogen has 1 single covalent bond, which is what satisfies hydrogen's octet rule. So this is the correct structure for the NH4 ion. As maybe is the theme as always in chemistry, there are some exceptions to our octet rule. The octet rule is not always the hardest and fastest of rules. It works really, really great for carbon, nitrogen, oxygen, chlorine, bromine. It's almost infallible for those guys. But for other atoms, there are exceptions. There are differences sometimes in the octet rules. The first difference that we see are some of the small atoms, boron and beryllium in particular, can really achieve stability because they're so small with less than 8 valence electrons. Boron is famous for being able to achieve stability with 6 valence electrons. And beryllium can form some covalent compounds with just 4 valence electrons, as you can see in the example shown here. BF3 is boron trifluoride, BeH2 is beryllium dihydride, and both of these are actual insoluble molecules that we have discovered, studied, and captured in the lab, so we know that they're stable compounds, and they're just some exceptions to the octet rule. We also see you will run into cases where you have odd electron molecules. A great example is nitrogen monoxide. Again, this is a real molecule. It has been captured and studied in the lab, so we know it exists. However, if you try to draw the Lewis structure for it, you would figure out there are 11 valence electrons with which to work, and that's not going to be able to give you a structure in the Lewis structure where everybody has a satisfied octet. So when you run into this occasion, what you do is you make sure everything gets the highest amount of electrons possible without going over 8. And then the less electronegative element should be the one missing out. So in our nitrogen monoxide example here, we see that the nitrogen, if you count how many valence electrons, he has 2, 4, 6, 7, while the oxygen has 2, 4, 6, 8. And so that uses up, all 15 electrons are used there for that molecule, but nitrogen really only has 7. You may ask why you can't slide one more pair of electrons from the oxygen over into a triple bond, and if you did that, that would actually force 9 electrons onto the nitrogen. And while we may see some molecules where the octet rule is undercut, like we do here with nitrogen only having 7, nitrogen and oxygen and carbon never go over the octet rule. They never go over 8 electrons. They are not big enough. So they can't break the octet rule that way. They can, in some cases, really particular cases, have less than 8. And when they do, you try to get them as close to 8 as possible. And the least electronegative element should be the one missing out. Oxygen wouldn't miss out here because he pulls the electrons to him. With that said, there are some of the larger atoms, further down the periodic table can exceed the octet rule by using their empty d orbitals to bond. The famous ones that we'll see in some of our example are sulfur, phosphorus, xenon, and iodine. Xenon, in fact, is one of our noble gases, and we usually say they don't bond, but those d orbitals it can use to form some exotic compounds. These atoms are large enough they can form 5 and 6 bonds, and so if you run into Lewis structures where you have a ton of electrons and one of these atoms, use that atom as the central atom and throw any extra electrons, whether that be extra bonds or extra lone pairs at the end, go on those large central atoms to draw those octet rules. So that's the discussion for the Lewis structures. I hope that helps you understand how to draw and do these Lewis structures and get yourself some practice with them. As always, email, let me know if you have any questions or comments about the video and information presented here. Good luck, you guys, and see you later.